Okay, this is an advanced circuit. I recommend you watch the series and the parallel circuit analysis with the spreadsheet before watching this video. So here we have a circuit where all of our known values are the resistance values. So we know what all our loads are, and we know our supply voltage, and that's all. And we're told to do a circuit analysis on this. Well, the first thing you're going to do is look at which loads are obviously in series with other loads. So we could see that these three are in series with each other, these two are in series, etc. So if 1 and 2 are in series, to figure out total resistance in a series circuit, we just add them together. So we're given this virtual load between these two. And the next one we'll look at is 3 and 4. We want to add those two up because they're in series. Now, how do we know they're in series? Because if we were going to look at current, and we will, current is traveling through this load and it doesn't go anywhere else. And then it goes through this load. When that's a true statement, current stays in that same path. Hence the rule, current stays the same in a series circuit. Then I know these two are in series and I just add them together. So I've done that to give me this virtual load. Next, let's add these two. And now we're going to add those two together to give us this, and then add that to our 7 ohm because those are all in series, and that gives us this. Now that's the first step. We've identified all the loads that are in series with each other, added them together, and redrawn the circuit to give us what I call the virtual loads, the representation of each branch. Now, how do we identify the branches? Well, let's look at current flow. And by the way, the 10 ohm there, we don't do anything with that because it's all by itself. Right now, we cannot do anything with the 10 ohm. And identifying current flow will help with this. So with the red arrow here, we have current flow comes up and it gets to this branch. And there it splits. So some of the current's going through the orange path and the rest of it is going through the green path. And then when they come back together, they combine to give us the same amount of current that entered the branch. So whenever you have a feeder current come into a branch and split off and then recombine again, that is counted as a parallel circuit. So we can see here we've got a feeder current or total current. It's about to split off again, and I've used color codes, magenta and light blue, to show those two currents splitting off and then combining back here again. So we can say that these two loads are in parallel because the feeder current split and then recombined right here. So this is our total circuit current in red, and that's what's going through our 10 ohm or R10. So we can count 4 separate current paths or branches. We don't count our main or total current. We're just looking at where does that current split and then recombine. So we have 4 separate colors representing that. So now that I'm able to identify where that current splits and recombines, that lets me identify each of my parallel circuits. So in the red boxes, I have identified 2 separate parallel circuits. Now let's go to our spreadsheet. We're going to back up here a little bit. We're going to go back to the point where we started combining these loads. Now the first step in your spreadsheet is to identify what are your known values. And here, the known values I always highlight in yellow. These are the values that I could change in a spreadsheet, and the rest of the spreadsheet would do the work for me. Now, to save time, I created another sheet here to show you color coding. What I've done is I've color coded each load to represent those different colors of each branch current. So for instance, this one in magenta, we said was 3 loads in series. So if we look at my spreadsheet, we can see the 3 that are in series have that same color code. Okay. And we gave some virtual identifiers to represent these combinations. Okay, so we'll go back to that sheet, that drawing, and we're going to go to the point where we were simplifying or adding up these loads. So we did 1 and 2 together to give us this virtual load, 3 and 4 together to give us this one, etc. And then we traced out our current. Now we're going to give this one a virtual identifier of R100 and this one R200. And that's where this comes in. Now we said R100 is the series circuit of these two. So equals, I want to add this load plus this load. Now I have the virtual resistance of R100 equals this load plus this load. Now I have the virtual of this one equals these two in series, and this one equals these 3 in series. And R10 is all by itself, so we're just going to tell this cell, I want you to equal whatever's placed in here. Now notice that I have voltage, current, power for each one of these breakdowns, and I've done that for a reason. You're going to see how this all comes together. So I've given this some identifiers, and we traced the current and identified branches and parallel branches, right? Here are 2 parallel branches. Now, I don't have any other information, so I'm forced to use the reciprocal formula on these 2 virtual loads to calculate the total resistance in this parallel circuit. So that's 1 over this load plus 1 over this load, and then you take the reciprocal of your answer. So it's 1 divided by 25, 1 divided by 56, which translates to this, which translates to this. Then you take the reciprocal of that value, and that ends up being this. So the total resistance of this branch is this, and we give it an identifier, a virtual resistance identifier as R300. So we're going to take and do this in a spreadsheet now, and we got to remember this is what we calculated. So over here I created the virtual resistor R300, and R300 are these 2 in parallel with each other. So what I normally do is I just tell these cells, I want you to equal 1 divided by this value. And I want the cell below it to do the same thing. Let's reduce our decimal places here. I want the reciprocal of both of these loads. Now I want to add those 2 together. So I'm going to take the sum of those 2. I'm going to put that here. And I guess I should get my decimal places down to 2 decimal places is going to be good for this. Alright, so we want the reciprocal of this answer. That's going to be the resistance for that virtual load. So we're going to tell this cell, I want you to equal 1 divided by that answer. There's our 17.28 ohms, and, whoops, sorry, that is what we came up with for our 300. So it looks like our spreadsheet's on the right track. Now we've got these two virtual loads, which we've identified now, are 400 and 500. And that is shown right here, 400 and 500. We just added those guys up in series, remember, and came up with a virtual resistance value. But we didn't quite have the circuit reduced down to just a series circuit. So now we have to treat this parallel branch the same way we treated the one up here. So we're going to have to use that reciprocal formula again, which is 1 divided by this value plus 1 divided by that value, which equals that. And then once we get the answer, we take the reciprocal of that, and that answer is going to be the resistance of this parallel branch. Total resistance in a parallel circuit is always lower than the lowest resistance. Our lowest resistance is 9. Our answer is 5.88. Looks like we're on the right track. And then we're going to give this a virtual identifier of 600. So there's our 5.88 ohms. We are done simplifying this circuit because we've narrowed it down to a series circuit. Now let's look at the rest of our spreadsheet here. What I want to do is this same formula all the way down. I want to do the same thing for each row. So I can copy this cell and I could paste it here and I could paste it here. Now I need the sum of those two together right there, and then I need the reciprocal of that I'm going to put here. So equals, I actually could copy, I could, but I'm not. I'm going to do equals 1 divided by this value, and there's our 5.88. What's nice is the way this sheet is being designed is if I change any of the yellow cells so far, all of these will react to that change. So this is the reciprocal of that value, 1 divided by 9. This answer is 1 divided by 17. I added those two together, and then I took the reciprocal of that in here. Now, again, R10 is all by itself, so I can tell this cell I want you to equal whatever value is placed in here. Now that we've narrowed this down as far as we can, just a series circuit, let's treat this using Ohm's law. Let's treat it as a series circuit. So in my gray here, I want the totals. So to figure out total resistance in a series circuit, we just add them all together. That turns out to be my total resistance. If we go back to our circuit here, there's our total resistance. Well, I happen to know my supply voltage. So we have our total resistance figured out is 33.17 ohms. Now, for my supply voltage, I'm going to tell this cell I want it to equal whatever's in this cell. And in this cell, it's my totals. I want it to equal whatever's put in this cell. Well, right away I can see that I have total resistance, total voltage. We all know what I can do next. I can take my voltage divided by that resistance, and there is my total amperage. I might as well calculate total wattage. So I times E, and there's my total wattage. If we look at this circuit, we know that the current's the same in a series circuit. So what that means here is that the current in these two virtual loads is the same as our 10 ohm. If I take my 10 ohm and multiply it by that known current, I get this voltage, 72.36 volts. That's how many volts this one load is getting dropped across it. And if I take my supply voltage and I subtract that voltage, this is the remaining voltage that's going to be used on the rest of the circuit. So what I can tell this sheet, now that I know my total current, and I know the total current is the same for this load, R10, I can say, okay, look, spreadsheet, I want you to equal whatever's calculated in there. I'm going to go over to this amperage. I want you to equal whatever this total is. And I want you to equal whatever the total is, because it's all the same. Now I can do all the rest of the math for my lonely 10 ohm here. I can tell this I want you to equal resistance times current to give me that voltage drop. And I could do the same thing here. Resistance times current. That's what I have left. I might as well calculate the wattage. I times E for this. There's my total wattage across that 10 ohm. So that 10 ohm better be big. And I'm going to do the same thing here. I times E. And we could also do our supply voltage, or supply totals here. And they work out. So far, so good. Now, some people are saying, well, why are you typing that in when you can drag it down? Well, I have color codes here, and I want to keep the colors the same. So that's why I'm doing that. Well, if I know that this is the amperage across this load, and let's go back to our circuit here, and I know the amperage is going through these two virtual loads, R600 and R300, then what that means is I can put that current in this sheet. So I'm going to tell the sheet I want you to equal whatever this is, because this is our simplified series circuit here. And I want you to equal this current. Well, we all know when you have two known values, you can start solving for the unknown. So equals I times R. And because I don't have any colors, I can copy the cell and paste it. Equals, let's do E divided by, whoops, sorry. It's actually I times E, isn't it? Pi. And then we'll do the same thing here. And we can now cross-check our wattages. The same way I told you before, you could do this series or parallel. That includes a reduced circuit. So we calculated our total wattage here. We used the pi formula with the. We used our known values here to calculate wattage. So let's add up all our wattages and see if it comes out to be the same. So I'm going to take the sum of all these wattages, and lo and behold, it's the same. And that works for a reduced circuit, series circuit, or parallel. That cross-check always works. Let's go back to our circuit, and now that we know the resistance across this virtual load and the current, we can calculate the voltage drop across this R300. We can also do it across R600. So in our spreadsheet, we've done that. We have calculated the voltage drop across both of these virtual loads, 300, 600. And if we add those two together, this is the total. And what do you know? when we calculated this earlier, we took the supply voltage and subtracted what this lonely 10 ohm was using up, and there's what's left over. It equaled. Now we got to remember that this virtual load R300 is actually R100 and R200 in parallel. Our rules of parallel circuit says voltage is the same across a parallel circuit. So if I've calculated a voltage drop across this virtual load R300, that means that voltage drop is the same across 100 and 200. So we go back to our spreadsheet and we look at our 100 and 200 are in parallel, and we know that we want this to equal what we calculated here. It's the same. And we want this to equal what we calculated here, because these guys are in parallel. Now I have two known values. I can start solving everything else. Equals E divided by R equals E divided by R. This tells me the current in this branch, and this tells me the current in this branch. Now we can calculate branch wattage, or the total wattage in the branch. Might as well do that. We're going to do the pi formula. I times E equals I times E and we applied this here. This is the voltage drop across here. We were able to calculate the current in each branch. We got 5 amps in this branch and 2.23 amps in this branch. We have to remember though that these are two loads in series up here. So we have 5 amps going through both of these loads. Current's the same in a series circuit. We have 2.23 amps going through these two loads. Well, let's look at our spreadsheet and see how we can deal with that math. Well, we know that R100 were these two loads in series. And down here we calculated 5 amps. Notice the color codes are lining up too. So we're going to tell this cell I want you to equal whatever I calculate down here. And I want you to equal whatever I calculate down here. Same thing for these two. And now we know we can solve for everything else. I can tell the sheet now I want you to equal I times R to give me the voltage drop. I want my wattage to equal pi I times E. Now because I have color code here, I can drag this down and it will copy that formula for me for each row. And I want this one to do the same thing. So we went ahead and we made our spreadsheet solve everything we know right here, because we had all the information we needed to solve for everything here. So we calculated our voltage drops for each load. We know the amperage and the resistance. And if we were to add up these two voltages, they would equal the same thing as adding up these two voltages. So what I did in the spreadsheet was I continued with the pattern for those two branches, the orange branch and the green branch. Now that I know all that, I need to look at these two branches that are in parallel, and I've calculated a voltage drop of 42.58 volts. Now I did that calculation when I had this circuit simplified as far as I could. So this R600 had that voltage drop across it, and that gave me the ability to know that these two virtual loads in parallel have the same voltage drop. So let's go back to our spreadsheet and check that out. So we know that R400 is in parallel with R500. And that's where we got this R600 virtual. And there's our voltage drop that we figured out. This was our simplified series circuit, remember? So if I know the voltage drop, and I know these two are in parallel, that means the voltage is the same across those two. So I'm going to tell this cell I want you to equal whatever's calculated here. And I want you to equal whatever's calculated here. Well, now I can do the rest of my math. I can tell this that I want to take the voltage divided by the resistance to give me the current in that branch. And the same thing here. Take this voltage divided by this virtual resistance gives me the current in this branch. Now I'm going to do my wattages. I times Z, or pi, equals I times Z. And now I have wattages calculated for each branch, and these are virtual. But I told you we could add those up and get the same answer. So let's take the sum of all these wattages, including our 10 ohm, and lo and behold, it works out again. Now let's go back up to here. Now if I know the voltage across this branch and I know the resistance, I could figure out the current across this branch. So in our spreadsheet, my branch 400 here, my R400, was made up of these two guys, remember, in series. 5 plus 4 is 9. So I'm going to go ahead and translate the current that was calculated over to the current over here. So I'm going to tell this cell I want you to equal whatever I calculated here for my amperage, and I want this cell to be the same exact thing because these two guys are in series. I'm going to tell this cell I want you to equal whatever amperage I calculated there all the way down because all three of these are in series. And now if you've kept up with the other videos, you can see where I'm going with this. Go ahead and complete the math for my voltage drops across each load. We calculated the total current. Remember, in our current, we know that this equals whatever we calculated here. And now I can handle the rest of these cells. Equals I times R, there's my voltage drop, equals I times Z, pi. Okay, now let's look at our totals. Now we cannot go adding things up here. Remember, this was all broke down to a simplest form here to figure out all these totals. But we can take and add up all of our wattages. So let's do the sum of all of our wattages and see if we get the same answer as we did in all the other examples. And it looks like we did. And that's how I know the sheet's right. Now if I go back to our drawing, what we did was we calculated the amperage in each branch, knowing our virtual resistance and our voltage across each of those branches. And this is what the spreadsheet did the rest of. It kept to the color code, and it calculated the individual currents, voltages, wattages, and the whole sheet now reacts to changes in the yellow. So let's say somebody wanted to know, well, what happens if I reduce this voltage to 100? Well, I'm going to do that. I'm going to go in here and I'm going to change this to 100 and hit enter. And in a split second, this sheet changes to do a circuit analysis on this drawing all automatically down to the branches. and we could see that the wattages still add up. So I know that everything's working correctly.